So, everybody, welcome. Today we have an editorial for our interactive mashup. So, let's jump straight into it. Yeah. Actually, before we'll talk about the actual solutions, I'll just make some general comments. So, participation was quite high. We had 35 official participants, and a couple of people upsolved some problems. Yeah, some. And there were also people who solved a significant number of problems. So, including one legendary grandmaster, Max, who solved everything. Well, unfortunately, some of the participants knew some of the problems, but it's what's expected from Mashup, so nothing particular bad happened here. Um, Speaking of individual problems, first two problems were solved by most of the participants. The following two problems were also solved by more than half of participants, or approximately this number. Then problems E and F were expected to be of the same difficulty, but problem F turned out to be very difficult. In judging by the rating of the problem on Codeforces, it was expected to be easy, but my personal opinion about this problem is that it's hard. And as you can see, even LGMs can make wrong submissions on such problems. Although I think it's wrong answer one. Yeah, something went wrong with the format of output. Then after these two relatively difficult problems, there were two simpler problems. And there's a really simple reason for it, which I'll explain in a second. But then again, we see very difficult problems, well, I had a couple of solutions and even more attempts, right? But then JKL were difficult. Some of the participants knew L, so I think that Max and Purple Crayon they knew, but it's the only participants who solved it without knowing. I think it's CSQ 31. And then problem K was solved only by Max. Well, I also solved it while preparing the contest, obviously, but this is more real representation of the difficulty. And the reason is the secondary topic of interactive problem. It's important to understand what topics you can see combined with interactive problems. I tried to select problems that have different secondary topics to present a broad overview of what is possible to encounter in interactive problems. Let me jump into the problem set. So, first thing that you can see is just some implementation when you have to use a simple concept. You don't have to use anything complicated. You just analyze the queries that you have. For example, in this problem, we have an array. We can answer range some queries. And from this queries, from n such queries, where n is the length of the array, we have to restore the original array. Well, not a big deal. We know that we can restore element with index I plus 1 by asking queries from 1 to I plus 1 and from 1 to I and subtracting. So we can make all prefix queries. Then we realize that we have such condition, L less than R. So we actually make n minus 1 prefix queries. And from this, we are able to restore all numbers besides the first two, except the first two, right? So sort gets restored as sum from 1 to 3 minus sum from 1 to 2, and etc. And to restore first two numbers, we have to ask one more query. And because we can't ask one, excuse me, the natural prefix, the first subsegment that you can ask besides prefixes is from 2 to 3, and it turns out that you can actually restore first two elements. Like first will be from 1 to 3 minus from 2 to 3, and now in first and some from first to second you can restore second. So these first problems make use of simple concepts that you are most probably familiar with. And for example, I will go through second problem also, and I will take a look at the code of both of them. In the second problem, we had 6 numbers, and we can ask like what is the product of any 2, and we have to restore all numbers by using 4 queries. So obviously you can restore them like using 6 queries, I think. And the thing about these numbers is that all pairwise products are different. And once you notice this, you know that like by asking product, you actually get the pair, but then you don't know who's on which position. So suppose we ask 2 overlapping queries. So like first, second, and second and third. You get one pair, you get second pair, they obviously intersect by one element, so that element is second, and then you restore first and third. So actually you can restore, like if all pairwise products are distinct, and you have 3 n numbers, then you can restore the answer in 2 n queries. There are also different solutions to this problem, but like the main observation is that you can actually restore the product, the pair from the product, but you don't know the order. So for this, you need some more queries, right? And like one possible way to implement interactive problems is just the same thing, but don't forget to flush C out, right? And there are 3 possible ways you can flush C out. First is by printing std_handle. Second is by pushing std flush into the output stream. And the third is by calling the flush method of cout. They differ a bit. And you can use like any one of them. So this will be sufficient. But if you're extremely paranoid, then you can use all 3 of them. Like typically, interactive problems are not about super efficiency in terms of how to determine which queries to ask. But they're more like about how many queries do you ask. So that's it. So don't worry too much about the efficient, like how much faster one is than another. And well, the simplest way is just to output handle all the time. Yeah, I mean, like you have to output line break. So actually, like this alone, I think this won't be sufficient, but I may be wrong. So actually, if you want to use this, then you must probably also have to do something like this. And I believe that this can. No, I don't know which one is faster, to be honest. I think that the simplest way is just to print a handle. But I also decided to like show some other options that you can use here. So yeah, you can just write this thing all the time here when you have to ask a query, right? But usually it's more convenient to have them as a separate function. So you'll have a function that asks queries, and you'll have a function that outputs answers. Because like each of them has a specific format, and you don't want to duplicate your code. And by the way, you can like immediately exit from answer. to ensure that if you have like several if branches in each of them, you can answer the problem, and you don't want any more code to get executed accidentally, you can just exit from the answer function, which is pretty convenient if you ask me. So that's one possible way, and here we just do what I taught, what I said previously. Like, this is not the best way to implement this problem. I've seen some very cool solutions when we ask the same set of queries. So 1, 2, 2, 3, 4, 5, 5, 6, but we don't restore the permutation by hand, but instead we loop through all the permutation with std next permutation, and we just check whether a permutation is valid or not. This is obviously faster, that's linear, and that method is exponential, but you don't particularly care because there are only like 720 permutations. So you just check for each permutation that these 4 products match. And if they do, then you got the right permutation. So like, again, we see the use of this concept when you have like functions that ask and answer. Much later, we'll see another possible way to do it, and this is, of course, by Lambda functions. So if you don't want to like, go all the way here and implement a helper function, you can, of course, define it in the body of your program in the main function, like a Lambda function, right? And then you won't have to pass multiple arguments because you can just capture them by reference, right? So this approach has several benefits, I must say. And then you can just have the same implementation. So if your works here, if your implementation works when it's in the preamble, let's say so, then it will work as a Lambda function as well, just you don't have to pass all the arguments, you can capture them. So that's another possible way to implement. And all of these solutions are, of course, published on GitHub. So if you want to check out my account, then you can check it out. And problem C is, let me make sure. In problem C, we can ask, we have a permutation of length n, and we can ask queries like, what is pi modulo pj? And we are given 2 n queries. So 2 n queries sounds like we have to ask a pair of queries. And the simplest way to ask a pair of queries is like pi pj, pj pi. And it turns out that if you ask these queries, you can immediately restore the smaller number, I believe. And the reason for this is very simple. So for example, if we have like A is greater than B, then B modulo A will be just B, right? But A modulo B will be some remainder modulo B, right? So from zero all the way to B minus 1. When you realize this, you understand like this is smaller than this. So max of your answers is mean of the numbers. And then you can just, by asking question pi, pj, pj, pi, you restore the minimum in the pair. So then you can restore like all of them into n minus 2 queries, I believe. Just like the one you restored, leave it out and ask about a pair of numbers that you haven't restored yet. And the last number will be whatever is like not used in your set, because you have a permutation, so you know a set of numbers. And one way to implement is by using 2 pointers. So you go first index starts from left side of the array, second from the right. And then on each step, you restore whatever is smaller of 2 and move the corresponding pointer. So here, if move first and we move first, I mean, you got the idea, right? And the last number is like, well, there are multiple ways to restart. So one possible way is you know the sum of all numbers from 1 to n, and you know n minus 1 numbers, so the remaining should add up to this sum. So you get the condition like a sum of numbers that you already guessed plus unknown number equal this. If you take the sum of known numbers to the other side of the equation, you get the formula for the missing number. Or actually, I think this was extremely dumb of me because the missing number is length. Yeah, because we always remove the minimum number, right? Right. Always remove the smaller of 2, so well, the number that remains will be n, right? The largest possible number. Yeah, I think yeah, it got accepted. So yeah, this is actually the better way to restart. Like, if we always remove the smaller of 2, then we'll remain with the biggest number, which is length. So that's about this problem. Also, like, by the way, another profit of having this as a separate function is that you can work with zero-based indices in your main code, and then just add 1 whenever you want to ask query. And again, you avoid code duplication. So there are fewer places to forget this +1. Problem D is tree diameter, and it introduces us to another important, so actually the first important secondary topic for interactive problems, which is graph problems. There are many interactive graph problems, but this one is actually relatively simple. So here we have a tree which has at most 100 vertices. And what we want to find the tree diameter, as the title suggests. We can partition the nodes into 2 non-overlapping groups. Or actually we can select like 2 non-overlapping groups, not necessarily select all vertices, and find what is the longest distance between this and this. We want to find tree diameter in 9 queries. Now 9 log something like a log of n with some extra queries for some purpose. I think I actually never use more than 7 queries, but it does not matter. So once you realize that this is log, right, you then think like, I would like to ask several queries. And obviously the tree diameter is greater than equals to answers to all queries, right? But like, it don't necessarily equals the max of the answers if you ask wrong questions, right? So you may ask yourself a question like, how do I guarantee that each pair of vertices gets into different groups in at least one query? Then we'll automatically know what is the longest, what is the distance between these two, and we'll count it towards our maximum. So now you realize that you want to have like several partitions such that each pair of indices, for each pair of indices, there's at least one query in which they go to different groups. And the obvious way to do it is just like for every bit, add like partition on this bit. So that's exactly what I do. The query will loop over bits, so it's 1, 2, 4, 8. And if this bit is set, then we go to the first part. If it's not set, then we go to the second part. And we add the distance between this. Because all numbers, when represented in binary system, different numbers differ in at least 1 bit. And there are at most 7 bits in our number. So in 7 queries, in at most 7 queries, each pair of numbers in the bit that they differ, they'll go to separate different parts of the query. So we'll count the distance between them towards our maximum. So that's why it works. And so this bit masking sync is another important subtopic in interactive problems because it often allows you to do some things in logarithmic number of queries. So that's a nice thing. Then we have problem E, which has very complicated statement, but in fact is not all that complicated. We have a graph again, and it's a tree this time. So previously it was not a tree, it was a graph, but now it's a tree. Oh, actually this was also a tree, but it did not matter. For the problem. And then here we have another tree, and we have a special device that can output LCA of 2 nodes because the tree is rooted, and we want to figure out what is the root of the tree. We can ask n over 2 queries. Now, n over 2 suggests that we have to like discard 2 nodes from 2 vertices. So we have to like, during each query, we would like to get 2 nodes that we are sure that they are not root. And obviously, if you think like what happens when we ask about 2 vertices, right? If one of them is LCA of another, then another one is not a root, obviously, right? Actually, like if a vertex is not LCA, then it's not a root. You ask a question, you get some answer. If the vertices that you asked about are not this LCA, then they are not roots, right? You can cut them off. And then you may run into a problem. And if you just ask random queries, it may turn out that that the answer to your query is one of the numbers that you asked. So one of them is ancestor of another one. And then you can discard only one vertex, so you won't fit into n over 2 queries. How do you get around this problem? We want to ensure that like our vertices that we ask about can be LCA of each other. Can be ancestor of each other. Now, it turns out that we can just ask about 2 leaves, right? Because like leaf is rarely an ancestor of something. A leaf is an ancestor of something if and only if it's a root. Actually, when we ask about 2 leaves, we either discard both of them or we immediately figure out that one of them is the answer. That's exactly what I do. I have a set of leaves based on the degree. If degree of the vertex is 1, then it's a leaf, and then I just work with this set of leaves. I think that because of the way it's structured, it takes n log n time, but it does not matter because n is like up to 1000. And again, in interactive problems, the emphasis of the problem is most probably not on the efficiency of how you determine which queries to ask, but on the efficiency in terms of number of queries. So like, I believe there is a way to implement it in linear time if you prune the leaves in a smart fashion, but I'm not that smart, so I just... You don't have to think about the smart way. You can just remove leaves from the set. So that's exactly what I do. Like this part determines, like most of the time, this simply erases leaves. It erases leaves. Actually, it erases leaves straight away. If else is one of them, then it brings the answer. Otherwise, it has to recompute leaves. So despite this looks a bit complicated, it actually does like most of the work is maintaining the leaves more or less efficiently. And I think you can actually, because n is that small, you can actually fit something quadratic in, but I just found it more straightforward to get a leaf like this. That's why I used the set. Maybe it's not the easiest way to solve it. Like, either way, the emphasis is again on the number of queries. So as we see that sometimes you want to be familiar with graphs and trees and some of the concepts related to them. So like interactive problems sort of test your knowledge of concepts by making you ask efficiently queries. Now problem F, that's a string problem. Is it a string problem? No, that's okay. The string problem will come later. It's a strange device can do the following. You can ask k numbers and it will output m's of them in the format position and value. Actually, this is a complicated problem. It took me a lot to solve it. And the thing like you want to find the answer in n queries, or n is the length of the array, but you only ask k queries, queries of the size of k, right? Like, you may notice that k is smaller than n, and because otherwise you don't have much freedom in terms of what queries you can ask. Like you can only ask about the entire array, and only gives you one piece of information, which obviously can be used to restore the value of m. So this explains why k is smaller than n strictly. And the second observation that we can make, like how many queries we can actually ask if k is n minus 1. Turns out that we can ask n queries, right? And it's exactly how many we can ask according to the statement. So maybe we will be able to restore the array from k plus 1 numbers. And it actually simplifies things if you look at the examples, because here they do exactly this. And you may notice that they leave one out. So here they leave first number out, here they leave second number out, here they leave third number out, here they leave first number out. It's important to read sample tests, because this is actually a huge hint toward the solution. So once you leave one out and you see the responses, you understand like, if I leave a number which is greater than m's, and it won't change the answer. And if I leave the number which is smaller than m's, and it will change answer by one element. So like if you ask such queries, you will always get either m's element or m plus first element, and then you can just then you can just restore from this information. So you get m's element as an answer several times, and you get m plus first number as an answer several times. And m plus first number is the answer only when you removed one element from first to m's. So it is an answer m times. So we can just count how many times we get the maximal answer out of the 2 that we got, and this will be the answer. This will be the m. Now, it's really not trivial if you don't look at this sample, but with this sample, it's like, I'm surprised that they gave such thing. This problem is actually rated 1900 converses. I think like it's actually 2200, and like minus 300 points come from this sample test, because it's a huge hint toward the solution. Like initially I did not read it, and it took me like several hours to solve. But then I realized that they actually explained like half of the solution in the samples. So please always read the samples. They can lead you towards the solution. Another concept that occurs frequently as a secondary tag is like source and binary operations. And again, bit masks, right? So here we have like an integer x that is from 0 to the 14th minus 1. And then something. So like this is actually a strange problem, because like you give 100 numbers in this range, and they pick one index and they tell you the value of ax or x. So this is not like you ask 100 queries at a time. It's like you ask 100 queries and they answer one of them, whichever they want to, but they don't tell you which one, because then you obviously can restore an answer in one query. Here we have 2 queries. Then you have to think what is the connection between 100 and 2 to the 14th. And we realize again that 100 is smaller than 2 to the 7th, right? So I immediately thought about some decomposition of bits, of these 14 bits that x can have into 2 parts of 7. And I just realized that I can, like with these bits fixed, I can ask 100 numbers by varying these bits. So there is like 128 possible values for these bits. I just select 100 of them and ask. And because of this, like first 7 numbers are fixed. So no matter which query they pick to answer, like this part will be random, but this, I know this part and I know this XOR X. So I restore this part of X. And in the second query, I vary these bits and these are fixed. So I restore these bits of X. And the way I like implemented it here, the names are giant and baby, and they come from giant step, baby step chunks algorithm, which is like the general concept, I believe, is called meet in the middle, when you get some things from n to square root of n by using this decomposition, because each number can be represented as some giant number plus some baby number, where giant numbers are like multiples of something, in our example, multiples of 128, and baby numbers are like smaller than this first baby number, first giant number. So that explains the names if you didn't got it first, right? So yeah, sometimes because of this, you can actually like get even better than logarithmic number of queries. There's something like constant number of queries, which is really impressive. Then we have problem H, Omcar and duck. And here we have to walk a duck. We give a grid of numbers to Omcar, I'm sorry. And it can like, it asks several ducks to walk through this grid. He gives us the sum on the path, and we have to restore the path. And several test cases per board are for us not to get lucky. In case you're wondering why is that. So now I have to like, obviously we want all pass sums to be different. And if you start trying to build something like that, so like, okay, this will be the corner of our board. So I want all paths that lead to this cell to be different. Like I can use a value of 0 for it. Right? But if I use the value of 0 for this cell, then I won't be able to distinguish between this path and this path. So I actually want the value of 1 here. 1 is the smallest value that I can use. Here I can use 0. If I get 1 here, then this path will be 1 and this path will be 2. So I want this to be distinguishable from this. So I will put 2 here. So like this sum is 3, this sum is 2, this sum is, actually you probably don't see much. This sum is 3. This sum is 2, this sum is 1, this sum is 0. If you continue building like this, you quickly notice the pattern. Pattern is that here we have all zeros, here we have all ones. And then here we have numbers that go something like this. So here you will see powers of 2, and then everywhere else in the board, you'll see like this number is the sum of the above and to the left. So this suggests one way to generate the board, and I believe that this way numbers will be actually up to 10 to 2 to the 25th. No, because on this side they will get multiplied. Yeah, so you need like numbers up to 2 to the 5th. So once you constructed the board, how do you ensure that sums on all paths that end at such diagonals are different? So how do you restore? Like if you are in this cell, how do you know? Because you know like what path sums can be here and what path sums can be here, you can determine where to go. But how to do it quickly? Well, you can just, for each cell, the range of possible sums in it is actually the range, right? So it's continuous range. So for example, here we can have sums from 1 to 2, right? Here we can have sums from 4, I believe, all the way up to 6. But here we can have sums from 1 to 3. So when you are here, you know that here there are sums from 4 to 6. Here are sums from 1 to 3. So you check in which of the above and to the left ranges your sum fits, and you go to this cell and you can just go to parent all the time. That's exactly what I do in my code. So I have like actual grid. I have what is the lowest possible number, lowest possible path sum, and then in this cell, what is the upmost. It's a bit messy here, but I just wanted to be explicit. And then we just like check if we don't have, we can't go to up. If we can't go up, then we go to the left. We can't go to the left, then we obviously go up. Otherwise, if our weight fits in this interval from lower in the above cell to upper in the above cell, we go to the above cell. If it fits in the interval in the range of the cell which is to the left, we go to the left. And if it doesn't, then we exit with runtime error, which actually distinguishes it, I believe, from Bronken's verdicts. That we know like that for some reason we failed to restore the path. It's useful for debugging. It's like not what we want to get during the runtime. It's useful for debugging. So yeah, and again, notice the usage of Lambda functions. Because like it uses grid lower and upper. And you don't want to pass all of them as parameters to your function, so you can define a lambda that captures them. which is really convenient to use. Now we get to actually like very complicated problems, I believe. Guess the maximums. No, not yet. Here we have very complicated statement which explains how from one set using several more sets we generate some password. And the thing to notice in this problem is that like when we leave something out, let me actually remember what goes on here. When we ask queries, we ask what is the maximum number of some subsets of AI. And the password is generated as like maximum of a j excluding some of the sets. And if you think about like if you exclude only one set, and these sets are non-overlapping, mutually disjoint, right? Mutually disjoint. Because of that, you exclude the maximum of the entire array only from one set. So all entries of your password except one will be the same, which is not very secure password. Now we can restore this, like global max is just ask all. Once we know it, we have to find this one set, which contains the maximum of the entire array. And to do it, we can employ binary search. So we like partition sets into two halves, ask about first. If maximum equals to the global maximum, then this is not our half, we go to the next one. If maximum if maximum is smaller, then this is our half, and then we partition it further. And binary search is another important subtopic in interactive problems, because again, it allows you to ask very quickly. And the way to understand it, because you're allowed to ask 12 queries, which is approximately the log. Like in this case, both these queries are actually important. You have to, like, once you found this set, you have to ask about all the remaining sets, so rest. And you have to use first query to ask global max. So I actually use all 12 queries, and I believe there is no way to answer them quicker than in 12 queries. So again, like this is a hint towards the solution, a slight hint that you want something either with bit masks or with binary search. But in this case, like you can think about binary search as a way to do the same bit masking thing, we partition on each bit. Except for like in binary search, it's more convenient to partition it, so halves than partition on some bit. But it's more or less the same thing. This was not all that difficult. Then we have a string problem, and string problems are like not something you encounter very often, especially interactive string problems. And it has to deal with added distance. And like this is a very special problem. You won't encounter it often, but I decided to put several like very non-trivial problems in the end of the problem set for more experienced participants, and it turned out that some of them actually really liked these later problems. So I think it was a successful decision on our side. Here we have a very special string of length up to 300. We can ask any string and we'll get the added distance between them. We can't ask more than n plus 2 strings. So again, like, yeah, the thing is that they don't even give you the length of the string. So like first thing you want to do is restore the length of the artifact of this like powerful rune. And you can do it by asking a string that it's all A's and all B's, and it's longer than our string. Because like if you have very long strings of A's and some strings of A and B's, the fastest way to get from this to this is to change all B's to A's and to remove several A's from here. which if you think about is number of operations is equal to number of bits plus difference in length. Then if you ask about all bits, the number of operations will be number of a's plus difference in length. And because difference in length is the same for both squares, you can factor it out. That's exactly what we do here. So once we do it, we know the length of the string. And if you know the length of the string, you need some understanding of Levenstein or added distance. The thing is about it, it's like it's more or less stable in the following sense. If you change one letter, your distance won't change a lot, because it's always possible to change back in one operation and then perform the same change. So your distance will change at most by 1. And once you notice it, you can think like, okay, let me actually change in each position once. Right? So we have some initial string. Let's say we have string of all a's, right? But this time we have the correct length. And we alter first, and based on the result of comparison of distance for the first, we figure out what is actually what the letter should be here. Then we alter second. So we turn it on and off. And we figure out what is, but based on whether our distance increased or decreased, we can figure out what character it was. And we figure out for sort, for force, and for ends. And because you don't want to flip each bit separately, you can actually do it. Like, you can ask like all a's, and then first b in all a's, first like all but second are a's, and second is b, and etc. But this way you get n plus 3 queries, and the thing is that you can because you know the number of a's and number of b's, you don't have to ask last query. Oh, this is another thing that often occurs. Like, if you want to save one query, then you have to use some global information plus all but one or all but two restored elements to figure out what is the last number or letter or whatever. And this often saves you one query if constraints are like tight. And I said that we can figure out what letter is by the change in distance. And the truth is, like, if distance decreased, then your change was correct. For example, here I was changing to B, so my letter is B, because it got us closer to the answer. And if the change was not successful, then our previous letter was correct and our change was incorrect. So I add A because it was my previous letter. And another thing to mention is that in ask, there are some problems in which if you ask and you get you don't have to answer as a separate thing. You just have to for one of the questions to contain the correct answers. And again, we can use extra separate function for this purpose to exit immediately, or exit immediately with runtime error if we got something wrong, if we got incorrect response. I believe that on code forces, this will actually result in wrong answer because it's the exit code of your program and not of the interactor. But if you have interactor locally, then this will very well result in runtime error verdict, so that you actually know what went wrong, whether you get wrong answer or you just exceeded number of queries, for example. So this is it for this string problem. And again, you have to be familiar with some concept and employ your usage of this concept to ask queries efficiently. Problem K is geometry problem, interactive geometry, which is rare, very rare. The difficulty is 2300 rating, but only Max solved it during the contest. And well, obviously I solved it, and some people up solved it, I believe, but during the contest, only Max solved it, and he's LGM. So Nobody likes geometry. Like interactive geometry is just painful. But here you actually make use of very simple concepts. So you get area. You can ask area of the triangle, and you can ask the sign of the cross product. Now, if you're familiar with some geometries, and you know that sign of the cross product determines whether the rotation angle is clockwise or counterclockwise. And you want to restore the convex polygon. So you have, like, somebody gave you a convex polygon, but they give you some permutation of its vertices. They ask you to restore the correct order. And there are several ways to do it. But the main thing you have to understand this thing about cross product and like to the left or to the right, which way you rotate based on what cross product sign you get. And because of that, if you think about like one line from first point to second, and then you ask like what is the cross product of these two vectors, will tell you which way to go. So you can actually figure out what points lie on the one side and what points lie on the second side. This takes like n queries approximately. If you ask queries which are like second type, first vertex, second vertex, and then ace vertex. Then you would like to like do the same thing again, but if you divide and conquer, you will get n log n slash, right? So actually you want to divide along subset very smart. Now you can realize that actually what is the thing that you want to divide on? That's like the farthest point this way. The farthest point is characterized by area of this triangle being maximal. So you can then again ask all queries of such form. Ask area of this, of this, of this, of this. Then you will be able to select max, right? Then if you ask what is the angle, what is the sign of the angle with this, you will figure out who is here and who is here. And this is another n queries. If you do it on both sides, it becomes more queries. So here actually here the valid now. The first point is this one, I believe. Yes. So you got 4 quarters, and you actually ran out of queries. But if you think about it, you can actually already restore the answer. Because on this quarter, the areas that you asked previously, they are increasing. So you can sort by area. And here areas will be decreasing. And here areas are increasing. Because the area is base times height, and height increases. And here areas will be decreasing. So that's exactly what I do. And there are different ways to solve it. In first n queries, for example, you can determine what is the pair of consecutive vertices, and then just restore everything from it. That's another possible solution. But I will walk you through. First, we partition who is to the left and who is to the right of first pair of points. And then we ask all areas. Then we select what is the rightmost vertex, so the one with the highest area. Then we partition right into right bottom and right top, and we sort each one of them like in the right way. So here we got like increasing, and here we go like decrease. Then more or less the same thing goes with the left half. I didn't do it particularly well. Like a better way would be to factor this out into separate function, and then I just call it several times. But I didn't think for a long time about this problem. Once I realized this approach, so I just implemented this. So yeah, something like divide and conquer, but you save a lot of time once you partition in 4 quarters. But again, it requires like some knowledge of geometry that you can actually like partition to the left and to the right based on the sign of the cross product. But I believe it's like basic knowledge of geometry. And this thing with like most distant point from a line is the one with max triangle area. It's also like more or less well known. If you know some geometry, if you don't, then like you have to study some geometry, I believe. Because it's like around 2300, so it's not an easy problem. If you want to solve such problems, you're expected to have some knowledge of geometry. Then the last one is absolute madness. Because I can't actually prove like very rigorously that I make no more than 10,000 queries. It's number theory problem, and like you have a set from 1 to n. You can ask how many multiples of some number are in the set. You can ask the same thing, but then they get deleted, or you can answer. But the thing is, like, the hidden number is never deleted from the set. And this suggests that if you make 2 queries, then you can figure out whether x is divisible by something. So it has to deal something with factorization. If you first ask b, a, and then a, and you effectively get like whether x is divisible by a or not. So like idea is then to ask about small prime numbers. So I first ask about small prime numbers, which takes something like square root of max number plus log max number queries, which is already like a lot, I believe. Oh, no. This part is cheap. Okay, this part is cheap. But here we can actually ask about like powers of a prime to determine what is the largest power of the prime that this gets. This I forgot what I was talking about. I'm sorry, I got distracted by some important information. Yeah, so here we ask about small primes, and we figure out like most of the factorization of x. If we figured out that like we figured some of the factorization, then we can just ask for all large numbers. What number is it? And it takes something like off max over log max time, because there are that many primes. There are not too many primes, so we can afford asking this thing. And this effectively checks like if some large prime is a divisor of secret number. But if we haven't figured any of the factorization, then we have to do something smarter. And in this particular case, I actually had to refer to the solution by max. Because I kind of understood what we want, but it's just a bit too complicated. This problem is rated 2600, so maybe it's a little bit above my current level. I mean, it's a little bit too early to practice such problems, but I actually understand what goes on now. So you know that we have some large prime numbers, right? Our x is actually, I believe that our x is actually just one prime number, because it don't have small prime factors, so it must be one large prime number. And we can do binary search over these numbers. But sort of expensive binary search, because it will ask about like the entire first middle. You ask about the entire first middle, and you delete the numbers that are divisible by primes from the first half. If the result is such that by asking 1, you can actually get the number of remaining numbers. If it's equal to distance of, like to the length of right half, then your number is in the right half. You got right half. Otherwise, it's in the left half. And in fact, you can just ask about each number again. And whenever you hit it, you'll just get the answer. Actually, I believe that here is like it's simply the answer because x is one large prime, but something like this also works. I just was writing times equals all the time, so I'm just for the uniform, for the purposes of code being uniform, I just write times equals all the time. So yeah, that's a complicated number theory question, and you don't have to solve it if you want to just be overall not bad in interactive problems. Like actually, 3 last questions or so were mostly for people who just who are quite serious level already. If you're more like on the beginner level, then again, let's do make it a short recap of what you want to know. You want to know about binary search. So binary search is definitely a goal for interactive problems. You want to know something about graphs. Definitely want to know something about graphs and trees. You want to know something about bit masking, so that you can partition on bit. That's very useful. And potentially you want to know about XOR, like bitwise operations, all this thing. And from there it gets more difficult. From there, like once you know about simple concepts about trees, binary search and bit masking, variety of topics can arise as interactive problem, and you need some specific knowledge from this area, from the secondary area. Then you mostly do some construction to construct your number, whatever you want to find in the interactive problem. But again, like if you take a look at the standings, and like solving problems that don't require anything about strings, anything about geometry, it already gets you quite high. So it's like 7 problems you can solve. If you don't solve anything like super hard, and it's actually quite better than a lot of experts and specialists. So if you want like to be a candidate master, you probably want to be able to solve these 7 questions that Scarlett has solved. And I think it's more or less what I wanted to talk about this interactive mashup. So the main thing is that you want some general knowledge about binary search, bit masking, and trees. And if you face an interactive problem that is about a specific topic, then you need some specific knowledge of that topic. So it's like more interactive problems actually measure how good you are overall in some specific area, right? Not about like whether you can implement a specific algorithm yourself, but they measure your understanding of concepts such as Levenshtein distance, sign corresponding to the clockwise counterclockwise rotation, things like that. Yeah, thanks everyone for watching. I hope you enjoyed this interactive mashup. We may have more mashups soon. If I fail to find a good training on some topic, I may make more mashups. And this mashup was a success in my opinion. We got like 40 participants, including upsolving, and around 400 submissions. So a lot of time. Not only I invested a lot of time, but you guys also invested a lot of time in this interactive mashup and solving it. So I hope it actually made you better in interactive problems. And thanks for watching. I hope you have a great day in solving the questions, and see you next time soon. Bye-bye.